Thank you very much for the invitation to speak. It's a pleasure to give this talk, and I fondly remember my time at Makerere, also at Dar es Salaam, and in fact, I also spent a semester in Kigali teaching an algebra course that spring of 2009 as well. So let me start off by making a couple remarks. The first is, I'm actually not going to talk about my own work, although my work entirely centers on the absolute Galois group of the rational numbers. I'm going to just sort of tell a story as to why it's important and why we study this object and what we can gain from studying this object. So I'll focus more on other people's work. I think actually it's a good idea in colloquium talks to try and tell the big picture rather than talk only about one's own work. And as I mentioned earlier, I will try to monitor the chat, but if you have questions, either speak out loud, that's fine, interrupt me, or type them in the chat and I'll check, or if someone else notices, just let me know that there are some questions. All right, so let me begin. So I want to take two complex numbers, and I want to start off very nice and very easy. And here are some basic facts we know. So these are some basic facts about complex conjugation. Namely, you can do the addition first and then conjugate, or conjugate and do the addition, and you get the same answer. The same goes for multiplication, reciprocals. If you conjugate twice, you get the same number back, and a number equals its conjugate if and only if Z is an R. Now, what these say is that complex conjugation maybe, I'll even include this, is a field automorphism over the real numbers. Or another way of putting it is the absolute Galois group of C over R. There's a little more work that you have to do for this next statement, equals the identity map and complex conjugation. And its order is 2. Okay, so I don't know what the educational system is like in all the different countries you're in. In America, you will learn this maybe when you're 15 or 16 years old, but they don't tell you that you're learning Galois theory when you're 15 or 16 years old. But that is how it is. We're learning some basic Galois theory. And maybe what I'll remark here is that, of course, we all know this formula. Right, this is for solving a quadratic equation. Okay, but there's also a cubic formula. I'm not going to write it down. It'll take too long and take up too much space due to Ferro, Cardano, and Tartaglia. And there's a quartic formula. Oh, and maybe this was in the 15th century. And this is not even completely correct. I mean, this is sort of the Italian school. The cubic formula had been studied all over the world, in China and so forth earlier. But as far as we can tell from recorded records, the first complete solution was this one. And there's a quartic formula. Ferrari in the 16th century. And then, of course, it led people to wonder, what about the Quintic equation? Is there a general formula like this one with this cubic formula, of course, involves cube roots and square roots. The quartic formula involves fourth roots, cube roots, and square roots. Is there a general Quintic formula? And of course, Galois settled this negatively. Now, what does this have to do with the topic of my talk, the Galois theory of the rational number? Understanding Galois groups is going to be crucial at the finite level, even though we want to study this infinite one. And the problem is here, S5, the symmetric group on 5 letters, which is what the Galois group of your general Quintic, is not a solvable group. It has the simple constituent, the alternating group on 5 letters. And that's really the problem. Okay? So this idea that, okay, there's the Galois theory of C over R, there's Galois theory which helps resolve this question. And of course, it's important to note, the symmetric group on 4 letters is solvable. The symmetric group on 3 letters is solvable. And of course, the symmetric group on 2 letters, Z mod 2, is solvable. So that's why those problems were easy, and something fundamentally new happened at the Quintic. Okay. What's next? Now, for maybe 100 years or so, people studied the Galois group of finite extensions of the rationals, or even finite extensions of relative fields, K over L maybe. And it was sometime in the mid-1900s, maybe early 1900s, that people started to study all the extensions. And I was once at a lecture given by perhaps one of the great 20th century number theorists, John Tate, who passed away last year. And Tate said that in the late 50s, he was talking with Grothendieck, who is, I think it's safe to say, the father of modern algebraic geometry and the theory of schemes and étale cohomology and a whole lot of other stuff. And Grothendieck said, we need to do this, study all Galois extensions of Q simultaneously. And that completely revolutionized Tate's approach. And he started proving all sorts of amazing theorems about Galois cohomology and duality of Galois groups, which I'll talk about a little bit. But this is the idea. We want to study all of these objects simultaneously. So we make a definition. We take an inverse limit over all K of these finite Galois groups. Now, this thing is large. It's uncountable. Now, I should make a remark. It's naturally contained in the bijections from Q bar to Q bar, because an automorphism of Q bar, the algebraic closure, is just a bijection between these two, but it preserves the arithmetic. All those formulas I wrote down for complex conjugation have to be preserved. And this is countable, this is countable. The bijections from a countable set to a countable set is uncountable. So maybe it's not surprising that this thing is big, on the one hand. On the other hand, it isn't remotely equal to this set of bijections, because that's just a set theoretic thing, and we're putting a lot of structure on these, and it's still uncountable. That, to me, is a bit surprising. It has a topology. It is compact. And I won't go into too much of the details, but it looks like a Cantor set. It's compact and totally disconnected. So it's a very strange object. Strange looking if you don't spend your time thinking about these things. And a thing I like to say about it, which is open to dispute, I think, but I think that can be healthy, a little bit of dispute. MIOM that it is the most important object in mathematics, and reasonable people can disagree about this for sure. I would put the Laplacian as perhaps also one of the most important objects in mathematics, but I think it makes interesting discussions to think about what mathematical objects are so fundamental that everyone should sort of spend some time trying to understand them. And I would say that this group falls under that category. Now I want to do an aside first for a bit. To topology for just a minute. So let's have a Riemann surface. So this is the one I've written down. That here has genus 3. It has 3 holes. You could also study something with genus 0, a sphere, or an elliptic curve, a torus, something with genus 1, and so on. And there is a theory that says, call this thing X. If you do the cohomology theory, there's an Euler characteristic. And this Euler characteristic depends only on the genus. It's 2 minus 2g. Now, in fact, it's much more than that. We know the dimensions of each of these objects. This one is 1-dimensional, this one is 2g dimensional, this one is also 1-dimensional. So fine, we understand this. Now, what does that have to do with this group? Well, a moment ago, I told you the story about Tate, and I mentioned how after being inspired by Grothendieck, he proved all sorts of beautiful theorems, including duality and their cohomology. So I don't even want to define group cohomology. I will just say this, that GQ, let's just say it acts on a vector space V over the field of P elements. P is a prime, of course. So that can naturally happen, right? A group can act on a set, on a vector space, and so on. And then what we will find is that These cohomology groups, which I'm not defining, they're alternating cardinalities. H0 and H2 are positive, just like these ones are. Of course, here I'm taking dimensions. Here I'm taking cardinalities. I could have written that in terms of dimensions. With H1 in the bottom, that's what's happening here, H1 negative, that it becomes an easy to calculate object in terms of M, but it's also fair to say that these are separately very hard to calculate. So there is a difference between the Riemann surface situation, that cohomology theory and this cohomology theory, in that all three terms are easy to calculate here. And here, this one's easy. The Euler characteristic is easy, but these two individual ones, all you get is their difference in size or their ratio of sizes. And that's just life. And it's hard because number fields are not principal ideal domains. That is the primary reason this is hard, that they have what are called non-trivial class groups, which I'm not going to get into. But hopefully you see the beautiful analogy, right? That there is a nice Euler characteristic where this side, at least, in the Galois side, is easy to calculate. Okay, so we're realizing that this group kind of behaves like a manifold or like a Riemann surface. And I have a line that I like to use when I'm teaching a class where I say this is important enough to write down. So I think that's important enough to write down. G. At the finite level, when you were just studying the finite groups, this doesn't happen. They're just arbitrary finite groups. There's no beautiful theory. But when you take the inverse limit and you look at all of them put together, then there is a really nice theory. And I've told some small untruths here. You actually have to work with an appropriate quotient of GQ that is still infinite depending on V, but that's not worth getting into. You have to restrict ramification. Otherwise, the cohomology groups, the H1 and the H2, will both be infinite. But you can restrict and make them finite, and then this formula holds. Okay. So let's get back to the topic at hand, and I want to write down a Diaphantine equation. We'll see it again later. So here's a Diaphantine equation, y squared equals x cubed minus 2. And here's a solution. X is equal to 2. 2 cubed minus 2 is 6. Y is equal to root 6. Okay. Now, here's another solution. This one's more fun. 3 and plus or minus 5. By the way, it's a non-trivial exercise, but this is the only integral solution to this Diaphantine equation. Okay, it takes a little bit of work to prove that. You need to know that Q adjoined the square root of -2 is in fact a PID, but it's a fun exercise if you've never done it. Now, of course, what's the difference between these two solutions? If I call this object E because it's an elliptic curve, this is a solution that lives in the rational points of this elliptic curve, and this is a solution that does not live there. Now, if you take this solution, you know, without too much difficulty, now, that's the same thing I wrote here, so why am I making a big deal about it? Well, the answer is that we know that there is a field automorphism that switches root 6 to minus root 6. Okay, like a plus b root 6 goes to a minus b root 6. It's just like complex conjugation that we started with. And what the point I want to make is that 2 comma root 6, it does live in the points in the algebraic closure, because root 6 is an algebraic number. But then when you look at those points and you say, let's look at the ones that are invariant under this Galois action. So if you put if a group acts on something and you put the group up here, you're looking at the invariance, then it's not invariant because there's an element of the Galois group that swaps these solutions. So what's the moral? We'll write down this. That this Galois group knows the solutions to all Diaphantine equations. Just take the algebraic solutions and take their invariants. Of course, that's hard. I mean, it's not easy to figure this out, but this is the case. It knows the solutions to all Diaphantine equations. But I want to convince you this is a really hard group to understand. So this is an open problem, the inverse Galois problem. And what it asserts is that given G finite, a finite group, there exists an extension K over Q that has that as the Galois group. So for instance, Z mod 2 is not hard. The symmetric groups are not hard. Hilbert did the symmetric groups. The alternating groups are harder. Hilbert did those about 120 years ago. Cyclic groups are not hard. So where is this known? This is open. But it's known for lots of groups, some, but not all. Symmetric groups, alternating groups, cyclic groups. It's worth mentioning that for cyclic groups, the proof I know uses Dirichlet's theorems on primes and progressions. There are infinitely many primes of the form 1 mod 20, and which is a deep analytic result. It's about the non-vanishing of an L function. And it's worth pausing here. Earlier, when I was on this side, I drew the analogy with topology and the cohomology theory of Riemann surfaces to the cohomology theory of this group. And now we're trying to figure out what its quotients are. So maybe I should say this is the same as having a surjection from the absolute Galois group to your finite group G. And to prove that you can do this just for the most basic types of groups, cyclic groups, you need a deep analytic result. And then it was known for P groups by Schultz and Reichardt, and then solvable groups by Shafarevich in 1954. A small mistake for the 2 part of Shafarevich's theorem was found by Schmidt. Shafarevich fixed it in 1989, which, as far as I'm aware, might be the longest gap between a theorem having a mistake and being fixed by the original author. From 54 to 89 is 35 years. Usually it's someone else who does it, who creates the fix when it's that sort of time scale. Okay, but let me just sort of tell a story. I said these are simple groups. And there are classes of simple groups, right? There's a classification of finite simple groups. They live in families. There are some exceptional groups, and so on. We really do not know the inverse Galois problem for the next class of simple groups, which are the projective special linear groups. And it's worth remarking that if you do the two-dimensional projective special linear groups with a field of p elements. Now, what do I mean by this? Well, let me just say what this is. This is easier. This is the 2x2 matrices over Fp, the field of p elements with determinant 1. Okay, so that's a relatively basic object. And this is SL2 mod plus or minus the identity. And that's a simple group. That's a relatively standard exercise. Around 2010, my Cornell colleague, David Zuina, settled this question and showed that all of these groups were Galois groups over Q. Before we had it for, let's see, where did my notes go? We had it in 1974 by Xi for 7/8 of the primes. Mala in 93 got 15/16 of the primes. Clark in the 2000s got 31/32 of the primes if you are assuming the Birch-Swinnerton-Dyer conjecture, and you can see that this is like a Zeno's paradox. They weren't going to get there. They were always going to get halfway closer. But Zuina came up with a new idea and just settled the question. But it's worth remarking if you look at the field of 13 elements and you look at not the projective special linear group, but the special linear group, the problem is still open. This is not such a horrible group, and we do not know the answer here. There are good reasons why these groups here are much harder than these ones that have to do with algebraic geometry and representations arising naturally from algebrogeometric objects, and such things wouldn't. That's why they're harder. And we don't have a coherent theory for understanding this. So this is a nice example of why this thing is hard to understand, right? That's what I was going to try and convince you of. Let me make one more convincing argument as to why it's hard to understand. Okay. I'm going to have a vector space, one-dimensional over the complex numbers. You can just think of it as C, and I'm going to let GQ act trivially on V. Right? A group can act on a vector space. This action is trivial. So, of course, you can think of this as a homomorphism from my group to the automorphisms of my one-dimensional vector space, to GL1 of C. And in fact, every element goes to 1, right? Because it's a trivial action. So here's my claim. You may think you understand this, but you don't understand this representation. And that should strike you as strange. How can I not understand the trivial representation? Well, let me explain. So I'm going to again have to tell small inaccurate things, but they are basically in spirit correct. Inside here, for every prime P, there is an element associated to that prime. Actually, it's a conjugacy class, and it depends on this representation, and it only exists for almost all the primes, but let's sweep that detail under the rug. And of course, under this map, sigma p will map to some number alpha p, which is of course 1, because everything maps to 1, but I'm choosing to write it as alpha p. And now what I want to do is form this function from the representation. We have a representation, we're building an analytic function. And the analytic function we get is Riemann zeta function. So my argument is, if you believe you understand this representation completely, then you're telling me you understand Riemann zeta function completely. And I'm skeptical of that. Let's see, is there anything in the chat? Okay, something about the most important object in mathematics. Okay. Anyways, of course, this we know is defined for a real part of S bigger than 1. That's a calculus exercise, really. And that it analytic or meromorphically continues to C. And it has a functional equation. You can prove the meromorphic continuation via the functional equation. You can actually get the meromorphic continuation one step at a time. There are various ways to do this. But by the way, again, it's interesting. Earlier, I said you can solve part of the inverse Galois problem for cyclic groups using Dirichlet's theorem, an analytic result. Now we're studying a purely algebraic thing, a group acting on a one-dimensional vector space, looking at this representation, and we get an analytic object that tells us about the distribution of primes. If you studied the Riemann zeta function, you know the central question is, where are its zeros in the critical strip between real part between 0 and 1? They're conjectured all to be on the line, real part of S equals a half, and that is the Riemann hypothesis, to which we do not know the answer, and really have not made much progress on really in the last 80, 90 years. There's been small amounts of progress, but nothing that I would call really significant. So from a Galois representation, you form an analytic object, and that's going to be arising again. Let me see where we are for time. Great, 10 minutes. So let's go back to the elliptic curve, x cubed minus 2. Now, this is a symbol for the n torsion. Now, since this is a torus, it's just a product of two circles. And you know what the n torsion on a circle is. If it's the unit circle in the complex numbers, it's just z mod n, or the nth roots of unity. Similarly here, so as an abelian group, this is isomorphic to z mod n squared. And it turns out that these are all algebraic points. So GQ, the Galois group acts on them. And what we get is a representation. And what we will do, and this will seem very strange, but it turns out to be the right thing to do, is we'll let n equal L will be a prime. And we'll build a system of them it's not going to be a direct system, it's going to be an inverse system, and we'll get a big representation. And what happens to that special element, sigma p, that depends on the prime p? Where does it go? Well, now it has to go to a 2 by 2 matrix. So it'll go to something like this. And you form, just like we did before. And there's, again, small technicalities one has to deal with, but they aren't that important. These are not 1, by the way, which is why I wrote alpha p before, even though it was 1 with the zeta function, to emphasize that. And you get this. So you start with an arithmetic object, you build a family of Galois representations, Galois actions. You build this L function here, this very strange looking object. And here is the conjecture of Birch and Swinnerton-Dyer. Well, I need to make one remark first, sorry. So let me make the remark first. I'll make it over here. That the rational points are a finitely generated abelian group, some number of copies of Z in a finite part. That's the theorem of Mordell and Veit from the 1920s. So the conjecture of Birch and Swinnerton-Dyer is this, that the order of vanishing of this analytic function at s equals 1 is R, this rank. So this is rather remarkable. I'll write it down in a minute, but what are we doing? We're saying there's this Galois representation associated to this arithmetic object. We build this analytic object. The analytic object knows about the Diaphantine properties. It knows the rational solutions. Okay, and this conjecture has been proven in some cases. It's generally believed to be true, but the overall conjecture, I think, is out of reach. I mean, recently, with work of Bhargava and others, I think we now know that this conjecture is true for some positive fraction of elliptic curves, maybe 20, 30, 40% of them. But we don't know that it's true in general. And 15 years ago, we knew it was true for 0% of elliptic curves. So that's a big step forward. And Birch, Swinnerton-Dyer is one of the millennial problems, just like, the Riemann hypothesis. I mentioned that number fields are not PIDs, Sarah asks. Did you mean, yes, I meant the rings of integers of number fields, Sarah. Thank you. Yeah. So let me draw a little bit of a thing here. Where did this go? A little, yes. Now, before I actually summarize, I'm almost done, I'll finish in a few minutes. Right, I go till 10 of, I believe. Yep, great, I have 5 minutes. So there was the very famous work of Wiles and Taylor-Wiles in the mid-90s where they solved Fermat's last theorem and proved it was true. What it was about was there's more to it than this. They proved modularity, but that it had a functional equation and an analytic continuation. Now, we know this for the Riemann zeta function. We know it for Dirichlet L functions. Those are one-dimensional. So what I would remark is this is the two-dimensional setting. Zeta of S is the one-dimensional setting. So things that are one-dimensional, the representations are abelian. Things that are two-dimensional, the Galois actions and the representations can have non-abelian image. So there's a fundamental difference between those two things. And this was the first sort of non-abelian setting in which people were able to prove these results. And this, of course, allowed you to prove that elliptic curves are modular, and therefore, and that following from work of Frey, Rivet, Serre, said that Fermat's last theorem was false. Well, there were no solutions anyways, is the right way to put it. So maybe it's worth saying what has gone on in the last 25 years. Taylor and his school, and now Schulze and others, are pushing this much further. This was in the 1990s. Since then, this is not quite, I mean, there's many, many technical hypotheses that I do not want to talk about, but what we are studying are big representations, the L-adic integers, and we form our special element will go to a diagonal element, alpha 1 and alpha 2, alpha n, and we form the product over all primes, product and this is the L function. Well, not E, it's just some, let's call it L of S. And proving that these things have meromorphic continuations, functional equations, and the like. That's right. But it's worth mentioning what we don't know. Still, despite 25 years of marvelous progress, we don't know the zeros of these functions, just like we don't know the zeros of the Riemann zeta function still. You build these functions from these objects, and we still don't know everything we would like to. So let me finish up with two things. This thing feels purely algebraic, but to it, there are natural representations. Okay, and then from these, you get the analytic objects, the L functions. And these will give you Diaphantine information. The Birch-Swinnerton-Dyer conjecture tells you about the rational solutions to an equation. But this guy also knows the Diaphantine information. And what we're learning is going straight to the Diaphantine information from this group is hard, but this method is more fruitful. You have to sort of build all of these various objects, and then you can hopefully gain some knowledge about it. And maybe I will just end right now by saying, as I left graduate school, I was talking to my advisor, who happened to be Andrew Wiles, and I mentioned to him that my goal in life was to understand this object. I thought it was the most important object in mathematics. and I've been studying it ever since now for 30 years. And he responded by laughing and saying, understanding this object will take centuries. We have come a long way in the 30 years since I finished graduate school. When I finished, we sort of understood what was happening with n equal 1 in the abelian setting. Now we understand a lot more, but there's still a lot more to go. And the example of the inverse Galois problem for SL2 of F13, a pretty small group, indicates that we really don't know much about this group at all. Thank you very much for your attention.